Okay, morning, everybody. Still morning for another 10 minutes, technically. Please shut your laptops. You know the protocol. Be prepared. The only thing you're allowed to keep your laptops open for is the polls. The young lady there, can you shut your laptop? Rest of you guys, laptops. Kira, laptop. Thank you. Right. So we're going to be. We've completed our two series of lectures. Three, in fact. First was the introductory lectures, the first week. We went through 3 weeks on the topic of training neural networks. We've done two more weeks on convolutional neural network patterns. All of these had to do with different kinds of data. The basic neural network formalism is all about trying to detect a pattern on some static data. Convolutional neural networks were looking for position invariant pattern detection, but you still had the data all at once and you had to analyze all of it to make inferences about it. Now we are moving on to the next topic, namely time series analysis. So we're going to be talking for the next 3 weeks about recurrent neural networks. That is going well past the spring break. So
they weren't able to see the whole screen.
Okay, perfect. So can everybody see the slides on Zoom? Folks on Zoom, yes. Can you see the slides and can you hear me?
Yes.
All right, so let's begin, right? So there are many situations where we have to consider a series of inputs to provide the output. So, and the outputs too may be in a series. You can't just be analyzing every segment of the input. There are many vectors in. You need to consider the entire sequence of vectors coming in before you make your prediction. And the order in which, not just the vectors, but the order in which they come in also matter. So here's an example, speech recognition. You're given a spectrogram, which is just a sequence of spectral vectors. Our task is to analyze the entire sequence of spectral vectors to determine what was said. So you would need to see the entire spectrogram to decide that this represents the phrase to be, right? Or something like this. How many of you follow football? Okay. You are the rest of you, if you saw this text, the Steelers meanwhile continue to struggle to make stops on defense. They've allowed an average 30 points a game and have shown no signs of improving anytime soon. This appears every year, right? What sport is it about? Is there any clue? Right? You need to know a lot about the background information to know that this is really talking about football and not basketball. This could be a really low-scoring basketball game. This could be a high-scoring ice hockey game. You really don't know, right? The only thing you know is that the Steelers are a losing team. So that's text analysis. Something's going on. Someone who has your mic on, can you turn your mic off? Those of you with laptops open, please shut them. Please shut your laptops, right? Thank you. So,
sorry, Prof, you're muted.
We can hear you.
So we can't hear anything.
Please, can ETA notify the professor?
So, no, this is okay. Now I need to see the slides. Can you hear me on Zoom, guys?
Yes.
Okay,
Yeah.
perfect. Let's continue as soon as we can see the slides. Perfect. All right, let's continue. Right. So here's another case where we have to analyze the entire time series to make a prediction, predicting the
Excuse me,
stock market. So the
video
input
didn't
is
work.
now a sequence of vectors, and the vectors represent stock indices, stock prices for an entire collection of stocks, what have you. And the output is going to be a scalar, which could be a scalar, which is predicted stock value for a specific stock, or a vector where you're making predictions about a whole collection of stocks. Regardless, the point is, in order to make the prediction on any given day, you need to consider the entire past to see what the trends are. So again, this is a problem of time series analysis where you're looking at a series of inputs and you're making a prediction. So now, this is fun. Okay, now the slides are not moving. I think you should stay here.
Yes. I'll say for
Huh.
yeah, just take it now.
Okay, perfect. Okay. So in all of these situations, we have this problem. We have to consider a sequence of inputs, input vectors, and we must produce one or more outputs. And the prediction that you make, the value that you output, is a function of not just one input, but the entire sequence of inputs, and also depends on the order in which the inputs occurred. So this kind of time series analysis problem, obviously, this is still just a function. Something's going in, something's coming out. This can be done using neural networks. Now, before I continue, I want to introduce a representational shortcut over here. If you see the figure to the left, that's your standard MLP, except instead of drawing it face on, I've tilted it slightly. It's fully connected from layer to layer. If I continue to tilt it all the way so that it's edge on, it's going to look like the figure to the right. So every little square over there represents an entire layer of neurons. Every arrow represents a complete set of connections from all the neurons in the source to all the neurons in the destination of the arrow. So, for example, if I had a network of this kind, like the one that's shown on the left, the corresponding representation that I would have is the figure I have on the right. Or in this case, where I have two inputs going in, and the structure that you see to the left, the figure to the right is going to be the representational shortcut that I use for it. So this clear for everybody? Right. Because you're going to keep seeing this figure. If you see the figure to the right, you should not imagine that it's one neuron connecting to one neuron. It's a layer of neurons connecting to a layer of neurons. So let's return to our stock market problem. We have to consider the series of stock values in the past to make a prediction about today. Typically, if I want to make a stock prediction about how a stock is going to behave today, I want to see what happened yesterday, what happened the day before, and so on. So now if you were to compose a neural network for a stock market problem of this kind, what would the network look like? Who's number 4? Who's 4? Okay, yes. If you don't respond, you'll be marked absent. So how would you compose a neural network for this?
Maybe.
So I'm assuming you're speaking of something of this kind, right? You'll be considering 4 inputs today and the past 4 inputs in order to make the prediction for today. So this you're familiar with, right? Because if I want to make a prediction on any given day, say if I want to make a prediction at t plus 3, I'm going to consider all inputs from xt to xt plus 3. For t plus 4, I'd slide the whole thing one step forward. And t plus 5, I slide the whole thing one step forward, and so on. So we have seen networks of this kind before. What is this? That's just a TDNN. It's on slides, right? So this is a finite response system. What do I mean by that? something that happens today only affects the outputs for a finite window of time into the future. So for example, if the output depends on the input at time t and all the past inputs until time t minus n, then something that occurs on any given day is only going to influence the output for n days into the future. So to see this pictorially, consider the input that is shown in red. As my analysis slides forward on day t, that particular input is going to influence the output. It's going to influence the output at t plus 1, at t plus 2, at t plus 3, and then what happens at t plus 4? It no longer influences the output. So the window of time for which any input influences the output is finite. In this case, it's going to influence the output for 4 instants of time. So this is a finite response system. Now, would something like this be sufficient to predict the stock market? Why not?
Because it needs more, as you progress ahead in time, you need more data points from.
So you have the stock market has trends, right? So you have daily trends, you have weekly trends. To account for it, I can increase the number of time instants in the past that I look at it. But then, and so if I want to look at more of the past, I can just keep increasing the span of input that the predictor looks at. But then is this going to be sufficient for a generic situation? Who is number 100? Who's 100? Okay, someone in class is absent. Who is that person? Who's 100? So check your numbers, guys. Mark 100 is absent, please. Okay. All right. So what was my question? Okay, so you guys pay attention to me and also keep track of your numbers. If I want to, can I just continue to increase the amount of history that I will consider by increasing the width of the input, the span of input that I consider? So can anybody else answer this question? Yes.
No, because if you make it long enough that it's complex enough to make an accurate prediction, the stock market over time will always go up. So it'll just always stay up.
It's actually even worse than that, right? So what are the kinds of trends that you see in the stock market? You see daily trends. Something that happened today is indicative of what's going to happen today. Yesterday is going to be indicative of what's going to happen today. You have weekly trends. The stock market peaks on every Friday, right? Before the whole thing kind of shuts down. You have monthly trends. The day on which people get their paycheck is when they actually go to the market and buy stuff. You have seasonal trends. Every time the season rolls over, people are going to go and buy their winter clothes or their swimsuits or what have you. You have annual trends. The consumption peaks at Thanksgiving. It's going to go up on Christmas. Now, if you want to capture all of these trends, the history that you would want to look at is going to be infinite. How many parameters will you need for, even if it's not infinite, if I want to look back 2 years, if I want to capture annual trends, how many parameters will I need for something of this kind? A lot, right? In short. So I want one of you over here. Who's number 135? Someone is 135.
Yes, Professor, I'm on Zoom.
Okay, so can you suggest for me a solution? How do I fix this? I want this network to consider all past inputs, but I don't want it to have infinite parameters. By the way, can you guys with your open laptops, can you shut them, please? It's just distracting. Yes. Can you suggest something?
We can get input from the previous layer.
You can get inputs from the previous layer. Okay, guys at the back, do you mind shutting your laptops? Shut the laptops, please. Thank you. Right. So here's what, there's a poll.
polls published actually.
So can you not find the polls? Okay, fine, right, too bad. Saves me time. Convolutional neural networks are finite response systems because they're only looking at a finite span of the input, right? On the other hand, okay, make sure the next set of polls are up. No? And in a convolutional system, an input at time t is only going to affect the output for the duration, for a duration that is equal to the width of the window, input analysis window. Beyond that, it's not actually going to affect the output. So these are not sufficient models. So what we want is an infinite response system where something that happens today continues to influence the output forever and ever and ever. And here's one very simple way of doing it. I can say that the output at time t, yt, is a function not only of the current input xt, but also the previous output yt minus 1. Now, clearly, yt minus 1 carries information about xt minus 1. So it has information about the past input. But then yt minus 1 was in turn a function of yt minus 2, and so on, and so on, and so on. And so eventually, the prediction at any time is going to be dependent on every single input that ever went into the system. Something of this kind is what is called a Knox network, nonlinear autoregressive network with exogenous inputs. It's autoregressive in the sense that it's actually, it is considering past outputs as inputs. It's regressing on itself. And the exogenous inputs represents xt. So it's not just a function of the y's, it's also a function of the x's. And let's see how this works. So this is a Knox net where the past input, immediately past input, goes back into the network. So this is what the computation is going to look like. At time t, it's going to take yt minus 1 as the input. At t plus 1, it's going to take both the current blue input and the previous output, and t plus 2, and so on. So this is the actual manner in which the computation is being performed. And if I were to show all of the connections simultaneously, this is the entire sequence of computations. Now, I'm showing many columns, but each column represents the computation, the prediction at one instant of time. Every column is identical to every other column. And now you can see how an input at, say, the leftmost corner, the blue box in the leftmost corner, if you follow the chain of arrows to see which are all the outputs it influences, you can see that there's a continuous arrow all the way out to the end. Therefore, the first input continues to influence the output forever. So this has the characteristic we want. This is an infinite response system, Iskara.
Do all of those networks are considered the same? They have shared parameters?
It's the same network. So this is what we're doing, right? At each time, yeah, I just drew all of them, the entire computation all at once, right? So this clear for everybody? Now, I'm not going to actually show the yellow box. I can just show an arrow directly coming out of the output layer, which is the orange box over here. This is the complete connection that happens, sequence of connections that happens. And you can see how an input at any time influences the output forever. Now, I'm not restricted to looking at just, even in this, I'm not restricted to looking at just the current input and the immediately past output, right? I could, if I so desire, look at several of the past inputs and several of the past outputs to increase the complexity and expressivity of the model. But there's still the fact remains that this is maybe an increasingly complex but infinite response system. So they're very popular for Knox networks. They're very popular for time series prediction like weather, stock markets. Those of you who are doing projects on time series analysis will be seeing some variant of Knox networks in your project. And this is useful for any phenomenon with distinct innovations which drive an output, where you have some very clear input X, which could follow some trends itself, which drives the output Y. Now, over here, can you give me a number? Who's 183? 183, you're on Zoom. Who are you?
Yeah, Professor Amazon.
Okay. So in this kind of system, where is the memory about the past inputs? Which variable holds the memory about the past inputs?
I think it's the gray one that's
I can't quite hear you. Can you come closer to your microphone, please?
yeah, is that better?
Yeah, not really, but still.
Oh,
Go ahead.
I think it's stored in the hidden layer here.
Anybody want to tell me where the variable is stored for? Yes, Suchi? It's actually stored only in the output, right? The memory of there is nothing inside the model itself that carries any information about the past. All the information about the past is packed into your output. That's what you're depending on to retain memory. So let's make the memory more explicit. It doesn't make sense. I could just manipulate the output value and produce something completely different because there's nothing structural inside the network that retains information about the past. I would like to be able to have some internal variable in the network that represents the past so that maybe I can port the network. I increase the expressivity of the model itself. So I'm going to introduce an explicit memory variable, MT, whose job it is to remember the past. So the memory MT is some function of all the variables in the input in the network, the hidden variables H, the previous outputs Y, maybe the current inputs X, and past memory. Clearly, what I remember now must also depend on what I remembered in the past. And now the hidden values in this network themselves are going to be a function of not just the current input, but also what is there in memory. Now in the Knox network, MT was the same as YT. So this was outside the network. Now we are trying to introduce some variable M inside the network that actually also stores state information about the past. And the actual output Y is just a function of the hidden state of the network. So this clear to everybody? Yeah, yes. We'll get that, right? So this is an older version. This is how people originally began introducing memory into the network. HT, so that's just a special case, by the way, right? But the earliest models were something like this. Michael Jordan, some of you might think of him as a basketballer. He's not. This is a different Michael Jordan. The rest of you might know him as somebody who worked with latent variable models, and he's currently a professor at Berkeley. But his thesis was on recurrent neural networks. And except it wasn't recurrent, what he did was this. Now remember that I can make the network output dependent on just the past output, the current output depend on just the past output, or I can make it depend on a certain number of past outputs, as we saw for the Knox network. What if I want to make it dependent on the entire sequence of past outputs? In that case, what you can do is to maintain a running average of all the past outputs. And so this running average of past outputs can now be fed into the network. And this was Michael Jordan's network. He uses that little black box over there, has simply maintains a running average of all the past outputs. The value at any time t is the current output yt plus some mu times the previous memory. And you can see that this is, if I write something of this kind, this is simply going to be running average of past outputs. So you had mt equals yt plus mu times mt minus 1. And this is a running sum of past outputs. And this was used as the input at the next time. So the memory itself has a fixed structure. Once again, although this is an internal unit to the network, it's not actually considered as, it's considered an input to the network. It's not considered as something that is part of the network itself. What is the distinction? The distinction is that when I'm actually trying to perform back propagation to train the network, the derivatives will flow downwards from the top, and they're going to flow into the gray box, and then they're going to stop at the gray box. There is no further back propagation through the gray box because that thing has is considered as just an additional input to the network. There's no subsequent, there's no direct notion of this unit being an integral variable within the network itself. So an extension of that, so that's not a hidden state. You haven't actually included on the Knox network. All you've done is gone from using the previous output to using a running sum of the outputs as your input, right? So let's actually take a step forward and maybe use an internal variable from the network as your memory. So this was what was introduced by this guy, Ellman, Jeffrey Ellman, back in 1990, where at each time he clones the hidden state. So the hidden state is shown in green. He just makes a copy of it at each time and stores it inside the network. And that is provided as an an to the next instant of the net, for the computations at the next instant. Now here, there's actually an explicit dependence on internal variables in the network, but this is still what is called a partially recurrent network, just as the Jordan network was, in the sense that the hidden variable is cloned, but each column is treated as something independent. So the hidden variable, instead of using the output from the previous time, he's just using the hidden variable from the previous time as the input to the network at the current time. So if you were performing back propagation, once again, it's going to come to the black box and it's going to stop. So these were the first two attempts at trying to introduce memory explicitly into the network. And so the story so far in time series analysis, models must look at past inputs along with the current input. If you're looking at a finite horizon of past inputs, that gives us a convolutional neural network. Looking into the infinite past requires recursion, and Knox networks recurs by feeding back the output of the network to the input. Then you have these so-called simple or partially recurrent networks, where they have some additional variables inside the network that are supposed to capture memory, but those are treated as inputs rather than as an integral, continuously updated and computed and updated variable within the network itself. So Jordan networks maintain a running average of outputs in a memory unit, and Ellman networks clone the hidden variable and store that as an internal memory variable inside the network. And these are partially recurrent because during learning, the current error is not back propagated past the memory unit. It stops at the memory unit because the memory unit is basically treated as an input to the network. So back propagation is blocked at the memory units in Jordan networks. It's blocked at this so-called context unit in Ellman networks. We have a problem. Hopefully these work. Okay, 5 seconds, guys. Yes. The Ellman networks are just using the previous hidden state. The green connection is the value in the green boxes, just cloned, right? No, that's an entire hidden state. It's computed from the green box is computed from the input and the previous. So anyway, going back, memory neuron networks have true recurrence. They don't, because you don't actually, you have no back propagation going back through the black boxes. So for example, you have no way of saying an error that occurred at time 10 must somehow influence the parameters that are used to compute the outputs at time 0. That back propagation is blocked. And that's something that you would like to be able to have. So ideally, the situation must be that if I have something out here, maybe I can go back a few more pictures. If I have something happening in the extreme right corner, that may be an outcome of some minor perturbation occurring way back input in the very first column. And these memory networks have no way of back propagating the derivative that far back to make sure that influences, minor influences, are carried forward all the way through time. So also, it is true that in both of these cases, you're sort of dedicating a neuron specifically to store memory. So they have incorporated some component within the model to store memory, but it's still not full recurrence. But then if I go back to my element network, how can I update that? How can I fix that? And the answer stares us in the face, right? So here, what I can do is, instead of just stopping the derivative, the green and the gray boxes are identical. The gray box simply clones the green box at each time. Why do I need 2 copies of it? I can simply read the green values directly, right? But if I'm reading the green values directly, that means I can actually back propagate derivatives all the way back into the green box. And that gives us what is called the actual fully recurrent model, which is the state space model. Now, in the state space model, we define a state variable ht, which is the state of the network. The state summarizes information about the entire past, and all memory about the entire past is in this state. The state at any time is a function of the input at that time and the state at the previous time. The output of the network at any time is simply a function of the state at that time. Any of you who's worked on control systems, for instance, is very familiar with this model. You represent the state of the system, which is recurrent, which is dependent. The state at any time depends on the state at the previous time and anything else that had happened. And the output is just a function of the state, right? So this clear to everybody? Now, if I were to illustrate this pictorially, what would it look like? It's going to look something like this. The figure on the top shows the basic unit. You have the input xt going in at any time. The hidden state ht is a function of xt and the hidden state at t time t minus 1. The output is a function of ht. So if you were to perform the entire sequence of computations, you can see how at the first time you get the first input and the hidden state, the initial value for the hidden state, and you compute the first output. But then at every subsequent time, the hidden state is a function of the current input. Every column represents its subsequent times, and you can see how in every column, the hidden state at that time is a function of the input at that time and the hidden state at the previous time. Now, defining a model in this manner requires me to introduce one extra parameter on top of the basic network definition itself. So who is number 112? What would that be? Pardon me? So if I want to define a model in this manner, I need to be able to define something extra, something that is required on top of just the network parameters. What would that be? How would I compute the output hidden state at time 0? So I need to have some initial value for the hidden state, h of minus 1. If I don't have an h of minus 1, then I have no way of computing by having this recurrence, I need to, I introduce this need to have this extra value h of minus 1, and that is what is used, will be used to compute the hidden state at time 0. So h of minus 1 is an extra input that must be specified, which is the initial state of the network. Now, the green box that I've shown over here, I'm just sort of showing a generic box. It doesn't mean that it's, if this were a neural network, it doesn't mean that it's just one hidden neuron. This is the state of the model. The state can be arbitrarily complex. So in a neural network, that hidden state can have itself have many, many layers. It can be an entire network all by itself. All that we are worried about is that it's a state unit, which captures the state of the system, which somehow captures not just what's going on currently, but what has happened in the entire past, right? And it can be arbitrarily complex. That state variable is going to have a bunch of internal variables itself, which are recurrently used. And in order for this model to work, the initial value for those recurrent variables, h of minus 1, must also be specified. So here's a very simple version of the model where my state is a single layer of neurons. If my state is a single layer of neurons, this is what the network is going to look like. Again, this is showing the entire computation. The network itself is just one column, right? And every column is identical to every other column over here. I'm just showing you the complete computation. And since the hidden state has only, the state has just one hidden layer, all I need to specify is h of -1 for that one layer. And now you can see how an input at the initial time is going to end up influencing outputs forever. I can have a more complex state of this kind, where the hidden state has two layers, in which case I'm going to have to specify the initial value for both layers, right? Or I can even have more complex connections of this kind. Again, remember that everything in between the input and hidden state. So the connections could be of this kind, where I not only have recurrent connections between the layers, but I have skip connections going from the bottom to the top. Or something even more complicated like this, where the first layer at any time t is feeding to the second layer at time t plus 1. The second layer at time t is feeding to the first layer at time t plus 1. And this is still a perfectly reasonable model, right? Yes.
What was the initial purpose? Why we shifted from output variable to state variable?
So the state variable is a variable within the network itself. The output variable is something outside the network. So it's not actually storing, the network itself is not storing any information about the history. You want variables within the network storing information about history. Right. So the output variable is just a single number in this case, for instance. So that was the point. And you don't need to have, yes. So again, the point, the real key to the model is this. You have a recurrent hidden state, and the recurrent hidden state can be arbitrarily complex, right? So these are just recurrent hidden states of different complexity. That's about it. Right? Now, I can extend this model. I can say that the hidden state at any time t is dependent not merely on the hidden state at time t minus 1, but also on the hidden state at time t minus 2. In which case I'd have a recurrence of this kind, where at each time, in this specific example, only the second layer, the hidden state, the second layer of the hidden state is dependent on the second layer of the hidden state at the previous time and the second layer of the hidden state at 2 instants ago. Now, in this case, you would correspondingly have to update the initial values that you're providing. You'd have to provide both h1 of -1, which represents the hidden state for the first layer, initial value of the hidden state for the first layer. You'd have to specify h2 of -1, which is the initial value for the second layer. And you'd also have to specify h2 of -2 because it's looking back 2 time instance. So both of those would have to be specified, right? The point being, all of the initial values must be specified for a recurrence of this kind to work. So when we speak of recurrent neural networks, typically we're going to stay with architectures of the kind shown on the slide here. Fairly simple and straightforward. They do the job more often than not, and they're simple to analyze and implement, right? But that doesn't mean you're restricted to using models such as these. Now, if you look at pictures and papers and books, you will find recurrent neural networks represented in this manner with this little looping arrow. That looping arrow doesn't mean that the output of the neuron is fed back to itself. It just means that the output of a neuron is fed back to that neuron at the next time. So I have 3 different architectures over here. The first one basically represents a recurrent neural network where the hidden state has only one layer of neurons, and the recurrence is of this kind. The second one is a little more complex. There are 2 hidden layers within the hidden state. And although the figure shows these with these loopy arrows, the actual computation being performed is the figure shown at the bottom of the slide. And this one, again, you can see how, although the point being that the loopy connection basically represents recurrence, right? So everyone with me so far, right? In terms of what we're trying to do, the point, what is, and also how we can represent it. Also, it must be very clear by now that every column in this bottom row is an identical network. It just basically represents the computation at one instant of time. So what is the actual computation being performed? So I'm going to represent that using two different notations. First, there's a scalar notation only for your reference so that you can go and look at the slides. But we know that it's much simpler to write this math using vector math. So let's look at it using vectors. Here's what the recurrence, the actual recurrence looks like for this simple model where the hidden state has only one hidden layer, right? The recurrence state has only one hidden layer. So over here, at the recurrence state, the computation at the hidden state has two steps. First, you compute an affine function of all of the inputs to that state, which includes, which is basically, if you go here, the inputs to the state include the current input and the previous hidden state value. So this affine term that goes into this green box is going to be some weighted sum of the inputs plus the weighted sum of the hidden state at the previous time plus the bias. Now there are two distinct sets of weights over here. The first one is the one to the left are the current weights. Those are the weights that are corresponding to the arrow going up. And then you have the recurrent weights. Those are the weights corresponding to the arrow going sideways. So there are two different sets of parameters for the hidden state. Once you compute an affine value, you're just going to apply an activation to it, typically a tan H activation. And the output of that hidden state, HT, is now fed to the output layer, where again, you compute an affine function of the hidden state and put that through an activation or softmax or whatever else. This is the computation that you'll be performing at each column. Now, if I have a network of this kind, again, this is the scalar version, here's what you'd have. Now I have two hidden states, two layers in the hidden state, right, in the recurrent state, right? So H1 is going to be computed as an activation applied to an affine function of the input and the first hidden state for the first layer of the hidden state at the previous time. So the first affine value function that you're computing is a weighted sum of x at that time, and h1 t minus 1, which is the first layer of the hidden state at the previous time, and of course the bias, and then you apply an activation to it. And then when you get to the second layer, the affine value going into the second layer is going to be a function of the hidden state at the same time, the second layer hidden state at the previous time, and the bias. So for the second layer, you find that the affine value over here, going in here, is a weighted sum of h1 at t, of h2 at t minus 1, and the bias. Yes. You can't see the mouse? Okay. Only I can see the mouse. Very great. And now I know what I was speaking about. No. Anyway, so, but again, I'm hopefully it was kind of clear what I was talking about, right? And then you're applying an activation. The equations are fairly straightforward. Now, tell me of, say, can you give me a number over here? Let's say, who's 87?
I'm on Zoom.
87. Okay. Which are on this slide, which are the recurrent weights and which are the current weights?
In this slide, the recurrent weight is W11, W22, and what is the other question?
So just W1 and W2 are the current weights, and then W2 at the bottom is a bug. That's going to be W3, right?
Yeah.
So you get the idea. Anytime the weights associated with the horizontal connections are recurrent weights, weights associated with vertical connections are the current weights, right? And you have several sets of parameters. Here is a more complicated model. So once again, if you look at the first hidden state is computing an affine function of the input and the hidden state of the previous time, and then applying an activation to it. The second hidden state is computing an affine value of the affine function of the output of the first hidden state, the input, and the second hidden state at the previous time. And the output again is an activation operating on an affine function of the first and the second hidden states, right? So, but then you get the idea, the general idea of how these things can be connected and what the recurrence looks like and what the recurrent and the non-recurrent parameters could be. So there are many variants on this basic model. These figures, I've taken these from Andre Karpathy's page. They show you different kinds of recurrences. That first picture on the extreme left, it shows you a network where a single input is used to compute a hidden state, which is used to compute an output. There is no recurrence, there's no looping, right? That's just your conventional NLP. The second picture is one where I have a single input, I have recurrence in the hidden state, and it's producing a sequence of outputs. So it's one input, many outputs. This is the kind of thing that you would have when you were doing a sequence generation. You're maybe providing a picture, it has to generate an entire sequence of text describing it. The third one is where you have an entire sequence of inputs and you have a single output coming out at the very end. So this is what you would have if you were performing speech recognition. The entire sequence of spectral vectors goes in. At the end, an output comes out. Or you could have something of this kind, delayed sequence to sequence. You have a sequence of inputs coming in, they're all analyzed. And then once all of the entire input sequence has been analyzed, that value is used to generate the entire sequence of outputs. So this is what you'd use if you were performing machine translation. You'd want to see the entire English sentence before translating it to French.
Is many to one similar to TDNN?
So no, because you have recurrence, right? So you have recurrence. See the connections in the hidden state? A TDNN wouldn't have the green arrows, right? And so then, of course, the many to many, where you assume the last one, where at each input, at each time, the network considers the current input and the previous hidden state and produces an output. In some sense, the last variant over here is a superset which includes all the previous ones. And so this is the one that we're going to be talking about mostly. And where necessary, we will show how it maps onto the other ones, okay? So here's the story so far. What we've added is that state space models retain information about the past through recurrent hidden states. These are what we call fully recurrent networks, because when you're training the model, something that happens way out into the future can end up influencing the updates you make at the current time. And for these cases, you also have to specify the initial value of the hidden states over which the recurrence happens. And very often this initial value for the hidden state is actually treated as a learnable parameter that you can also learn using backprop. And over here, the key piece of the state space models is that they enable the error at any time to influence how you update parameters way back in the past, going back arbitrarily, right? So we've sort of defined the network. But how do we train the network? Now, to train the network, we're going to use the standard paradigm. We're going to be given a collection of inputs and training instances, where a training instance consists of an input and a target output. The model of the network we're going to use is of the kind over here, where you have a sequence of inputs, and at each time you're producing an output. But the output at any time is a function not just of the current input, but a function of all of the inputs until that time. The dependence has been captured through this recurrent hidden state. And so your training data are going to consist of two sequences. Each training instance has an input sequence X and an output target output sequence D. So the input sequence represents the entire sequence of inputs. The target output sequence represents the entire sequence of outputs that you want the network to produce in response to the sequence of inputs. This collection, so you're going to have many such instances. This is not the entire training set. This pair of sequences represents one training instance. You're going to have many such pairs. And this collection of these pairs is your entire training data. So this is what you will use to train the network. Now, in response to any input sequence X, which is basically all the vectors in the sequence, the network is going to compute a sequence of outputs Y. We will compute a divergence between the sequence of outputs Y and the sequence of desired outputs D. So here is the entire unrolled computation. This is just, if I think about this, all this is really many repetitions of the same column, right? Each column represents the computation being performed at one time, but then you repeat the same computation at each time. So I can sort of unroll the computation and represent it in this manner. This is the entire sequence of computations being performed, but if you look at it carefully, you will see that X0 influences the output YT. So I could redraw this entire figure somewhat differently. I could have drawn it like so. I could have just said X0, and this is a hidden state, right? And then I have X1, then I can have X2, and then finally I can have YT, right? If I think of it this way, this is just a very deep network, sort of with skip connections from various inputs to the intermediate layers of the network, right? I've just drawn it out on the side. So this entire unrolled network is basically one giant network, but it has shared parameters, right? So who is number 48? Where is the network? Where are the shared parameters over here in the network? All the columns are identical, right? So any column has the same set of parameters as every other column. This is just a giant shared parameter network. This is what we're going to have to train. So we're going to use standard gradient descent. If I'm given a training instance, again, we're going to be computing gradients over we're going to be computing gradients for all the training instances. We'll compute the average gradients over the entire training set and use those to update network parameters. But then we're going to view this as a giant shared parameter network, and we're going to use the rules for training shared parameter networks when we actually train this model. So in the forward pass, for each training instance, you're going to pass the entire data sequence through the network, and you're going to generate all of these outputs Y. Then, so this is just the pseudocode for it. As you can see, you're going through time, t going from 0 to t-1 in this case. At each time, I've set the hidden state at time 0 to be the input itself just for convenience. You're going through the layers. At each layer, you first compute an affine value z, which is a function of the output of the lower layer in the network at the current time, the current layer at the previous, and the current layer at the previous time. And then you apply an activation to it. For the output layer alone, you have no recurrence because the output doesn't feed back in the simplest model, and you just compute an affine value and apply an activation to it, right? So now we're going to compute gradients, and we're going to propagate derivatives for the gradients through the network. This is the way we will do it. Remember, when I'm training a network of this kind, where did I put my chalk? Somewhere. So when I'm training a network of this kind, we're always start at the output and pass the derivatives backwards this way, right? If I unroll it and I do it vertically, this is what it looks like. And so your derivative to start out here and flow backwards, and this is actually going backwards through time because the progression of forward progression of information is through time as well, right? So because the derivatives are going backwards through time, this algorithm is called BPTT, or backward propagation through time. So I'm just going to sort of redraw the figure. Instead of drawing horizontal arrows just to make things explicit, I've drawn the arrows in this curved manner to show you that you have two outputs going out of the little green box, one going sideways, one going above, right? I'll use this modified picture and show you how the computations perform. The first thing you're going to do, you have the entire sequence of outputs Y. You have the desired sequence of outputs D, which is provided as part of the training data. You will compute a divergence between the desired sequence of outputs and the actual sequence of outputs. Again, this is not the sum of just the sum of the divergences for the individual outputs. What you're really, this is a sequence model. It's analyzing a sequence of inputs and computing a sequence of outputs, right? So the actual divergence is going to be a function of two sequences. It is not necessarily just the sum of the divergences at individual time instance, right? And so we are going to be computing the derivative of this global divergence, which is the divergence between two sequences, and propagating those two backwards. Now, it may not be clear what the distinction really is, but think of this, for example, as something that's maybe performing speech recognition. If you're performing speech recognition, it's going to output a sequence of words or a sequence of phonemes. The target sequence of words is going to be something different, very likely, right? The two may not even be the same length. There's no notion of one-to-one correspondence where I say this is the error here, this is the error here, I'm just going to add up the whole thing. So the divergence is really between two sequences. It's not the sum of divergences at individual outputs. This is something that you really have to remember, okay? And this will cause us considerable grief when we are actually training the models. So here is the notation. Yt is the output at time t. In this particular example, I just have one hidden layer of neurons, but it can have any number. We can generalize the example to more complex architectures. At each neuron, at the hidden layer, or at each layer, first you compute an affine value, right? So I'm going to indicate the affine value by the symbol Z as always. The superscript represents the layer. The term in the argument in parentheses represents time. HT is the output of the hidden layer. So this is after you apply the activation to the affine value. And so Z1T is the affine activation for the hidden layer. HT is the output of the hidden layer. Z2T is the affine value at the output layer. And YT is the actual output of the network at time t. So let's see how the computation is performed. I have some bugs on the slides, but I'm going to be representing the superscript W superscript 1. The second row is kind of messed up, okay? W superscript 1 represents the set of weights going into the first layer. W superscript 2 represents the set of weights going into the second layer. W11 represents the recurrent weights over here. So let's see how we perform backpropagation. Now we're going to start at the final time. So the very first step of backpropagation is to compute the derivative of the divergence with respect to the final output of the network, the one that's being pointed to by the green arrow. And now, remember, we are computing the derivative. The divergence is expected to be a function of the two sequences, the sequence of actual outputs and the sequence of desired outputs. Nonetheless, the divergence function must be differentiable, and we must be able to compute the derivative of the divergence with respect to each of the outputs. If you cannot do this, clearly you cannot perform backpropagation. So in the simplest case, if the divergence is simply a sum of the divergences at individual times, then this is very simple, right? The derivative of the divergence with respect to Yt is simply going to be the derivative of the local divergence at that time with respect to the output. But more generally, you need to be able to compute this term here, the derivative of the divergence, overall divergence, with respect to the individual outputs at every time. I'm going to assume that this divergence is computable, that the function is of the kind where the derivative of the divergence with respect to the individual outputs can be computed. In other words, I'm going to assume over here that the derivative of the divergence with respect to each of the y's can be computed. You have the formula for it. Let's start from that hypothesis, right? Now, if I'm working my way backwards, here's what will happen. So who's number 75? Who is 75?
Yeah.
Okay. So if let's assume that I have the derivative of the divergence with respect to all of the y's. So what is the first term I will be computing? Where will I begin if I'm performing back propagation?
I'll be getting it with respect to the final layer activation.
So this is first you would have to start the derivative of the divergence with respect to y of the capital T, right? So who's 62? Someone here is 62. Yes, wake up, right? So what is the next thing I'll be doing over here? We would capture, so from this is the final output. This is at time t. I have the derivative of the divergence with respect to yt. You want to compute the derivative of the divergence with respect to z of t, right? Final time. What is that going to be? Anybody want to help him there? What would that be? Someone, yes. So this is going to be simply the derivative of the divergence with respect to yt times the derivative of yt with respect to zt. What is that? That's just the Jacobian of y with respect to zt, right? That's the derivative of the activation at the final layer. So easy. We know how to compute the derivative with respect to the final value over there. Then I can take a step down and compute the derivative with respect to the output of the previous layer. So who is number 49? What would that formula be? So again, I want to compute the derivative. This is the final time, right? I want to compute the derivative with respect to h of t. Do we have 200 people in class? Okay. What is the largest number? 197. Who's 197? Yes. Yes. So what is the next term? If I want the derivative out here, what is it going to be? Somebody else want to help him? Pardon me? Dou z over dou h. What is that? So what is, if I want to communicate a derivative from here to here, what did we do for the MLP? We multiplied it by the weight, correct? Does everybody remember that? May I see you raise your hands to show that you do remember that? This should not have been a doubt, right? So the next thing I would do is to just multiply this by, I think I call that W2, correct? That gives me the derivative with respect to HT. And just to remind you, it's on the slides, right? Now, what is the other thing I would have to compute? Next thing. Who's 112? Who's 112? 112, it doesn't matter. Who is 112? Yes, Parth. What is the next derivative? But even before that, don't I need the derivative with respect to this weight? So what is that going to be? Anybody remember? How did we compute the derivative for the weight? So this is simply going to be HT is going to be H of T times the derivative of the divergence with respect to YT, correct? This is basically what we did going back. Very simple, going forward, backwards. So no biggie. We know how to compute that derivative as well, right? So who's number 21? Who is 21?
21. 21.
Okay, so what is the next derivative I would compute?
You'll be computing derivative of divergence with respect to the weight.
Your connection is really bad, so I'm going to give you a mulligan on this. You would want to compute the derivative with respect to the input over there, right? And how would you do that? You multiply the current derivative out here by the Jacobian for the next layer, right? The Jacobian of that activation. And then what else do I need to compute next? The derivative with respect to this weight, correct? And what is the derivative with respect to the weight? It's going to be the input times the derivative with respect to h, right? Very straightforward. There's one more derivative that remains, which is that the recurrent derivative, weights, right? So what would the recurrent derivative be? Pardon me? So that is simply going to be over here ht minus 1 times the derivative at the hidden state at the next time, right? So now I'm done with the final time instant. Let me begin working my way back to the previous time instant, right? Now at the previous time instant, I can do the same thing. I have the derivative with respect to yt minus 1. I can multiply that by the Jacobian, the derivative with respect to z minus 1. And then here's what happens. When I come down to the derivative with respect to h2 of t, h of t minus 1, h actually goes out two ways, right? One goes up vertically, one goes sideways. Correct? And so now the derivative is flowing in from two different sources. And so this derivative is going to have two additive terms. The first one over here is the derivative, vertical derivative, it just multiplies W2 on top. The second term is the horizontal derivative, which multiplies the derivative at time t by the recurrent weight, right? You see the two terms coming in, right? So this is easy. Now, what is the next derivative over here? So who is number, give me a number, 61. Yes. So what is the next derivative I'm missing here? But what about the weight? Have we considered the weight for the red arrow? So what is that derivative? So can somebody help her? What is the derivative for the weights of the red arrow over here? That's going to be ht minus 1, the value at the input to the arrow, times the derivative at the output of the arrow, right? But is that enough? This is the shared parameter, the same as the the corresponding arrow at the next time, correct? And so what you would actually have is that you've already computed a derivative with respect to W2 at the next time, at the final time instant t, right? When you were going down the vertical column at the final time, you already had a derivative. So the term over here is simply going to add to it. Was clear to everybody, right? What happened over here? And then, of course, I can go back down. I can compute the derivative there, which is simply multiplying the derivative for h by the Jacobian. And now what happens? What about the derivative for the lower arrow, W1? What is that going to be? So who is, give me a number, 10. Who's number 10? Yes. Is that it? Wait, but this, is it a shared parameter or is it not? I'm speaking of the derivative for the arrow that's for the weight square at the for the hidden state at so basically what will happen over here is going to be that the derivative for W1, you're going to have xt minus 1 times the derivative for z1 minus 1, but this is going to be added to the derivative that you got at the final time because it's a shared parameter, right? So same thing. Now, what about this guy? This again, the derivative here is going to be ht minus 2 times the derivative for zt minus 1, but that's going to be added to the derivative that we have already computed because it's a shared parameter, right? So is this making sense to everybody? Raise your hands if it is, right? I just want to make sure. Some of you are not, but okay. So, and now I can compute this, continue this process going all the way back to the very beginning. And then finally, at the very first instant, I can actually compute the derivative for hf minus 1. So since hf minus 1 is also a learnable parameter, I can use the derivative to perform gradient descent for hf minus 1 as well. Right? So questions, anybody? Here's the complete set of equations, starting from the end and going back. So who is number 33?
Yeah.
Who's yeah. So what were the variables we assumed we had in order to be able to perform this?
The previous hidden states.
So, okay, what were the, well, the question is bad. We assumed that we were able to compute the derivative of the divergence with respect to the output at each time, right? So long as you can do that, then you can perform the rest of the computation. So I have the slides over here. Let's get the slides. But this can be generalized to pretty much any architecture, right? There's one more poll. I may go a couple of minutes over, guys, but you'll have to bear with me. Okay, 10 seconds, guys. Yes. Actually, less than 10 seconds. Here you go, right? So if I were using stochastic gradient descent to train the network, it would be considering one time series at a time at a time instead of batches of inputs. And the corresponding equivalent for recurrent neural networks is going to be to update the network after each vector or each time series. Each time series, you'd have to take the entire time series, analyze the derivatives for it, and then update the network, right? So also, the divergence is the divergence between the sequence of outputs and the desired sequence of outputs and cannot necessarily be decomposed into the sums of divergences at individual times. Now, we're going to look at one extension to the network, and this is where I may go over a couple of minutes. We assume there was an implicit assumption in these models. And what was the implicit assumption over here? That the computation is from left to right, right? Suppose I gave you the entire sequence of inputs. Is there anything magical about going from the beginning to the end? There's no difference between end beginning to end and end to beginning, right? If I were thinking about it in terms of language, the word that I'm going to say now depends on the words in the past, but the word that I'm going to say now also influences the words in the future. So you could look at what words I spoke later to take a guess for what I said now, right? The dependence goes both ways. So let's extend our model. Let's actually have bidirectional recurrence. Now, the problem with bidirectional recurrence is that I cannot just use a network of this kind. If I've just used something of this kind where this influences this guy and this influences this right back, you're going to get this loopy computation, which will never end, right? So we're going to break this computation down into two distinct components. One is a forward component and one is a backward component. And so here's what the bidirectional equivalent of the network is going to look like. We're going to say our assumption is that the prediction at any time depends not just on the past, it can also be made based on the future. But the prediction based on the past is going to be separated from the prediction based on the future, and those two are going to eventually be combined. And so here's what the network looks like. Within any block, any layer of the bidirectional network, you're going to have two subnets. One subnet makes predictions from the beginning to the end. The other subnet makes predictions starting at the end, going back to the beginning. These are two completely different subnets. They have different sets of parameters. Each of them is going to compute its own value. And before passing it on to the next layer of the network, their individual outputs are going to be combined, usually just by concatenation. And so this is your bidirectional network. But then you need two different sets of initial parameters. For the forward network, you need HF minus 1, right? For the backward network, you need whatever initial value you will use after the end of the input. That's what I'm representing as H infinity. Both of these are going to be required as your initial values to perform your computation. And so once you do this, then the actual analysis within any block is going to be very simple. First, you'd have a forward net processing the data from 0 to t. Then you have a backward net processing the data backwards from t to 0. And then you're going to concatenate both of their inputs, their outputs, to form the output of the block itself. This will be passed on to the next block, and there are many different ways of doing this, right? You can have many blocks of these bidirectional structures, or you can have one bidirectional structure where both the forward and backward networks are arbitrarily complex, or you can have any combination of these. Doesn't really matter, but the basic idea can be understood by looking at just one bidirectional block, right? Questions, anybody? Any questions here? Was that clear? Okay, so now there's one final poll, and then I'll take a couple of minutes for backprop, and then we'll be done. I'm only giving you 30 seconds for this because it's just one question. All right, 10 seconds. That was very short, actually 5. Let me go ahead, right? So a day trader in the stock exchange to make RNN predictions, uses RNNs to make predictions from the historical market to decide which stock to buy. Can he use a bidirectional network? No, because he doesn't have future input. Bidirectional networks can only be used when you have future inputs to make predictions at the current time, right? Now, I have if you were actually implementing bidirectional networks, you wouldn't actually write two different blocks of code, one for the forward and one for the backward pass. You just write one block of code for performing forward inference. And to actually perform the computation, you're going to use the same code. You'd pass the data in left to right for the forward computation. You'd flip the data and pass the reverse data for the backward computation, and then you're going to flip the results right back to order them in the right way. So let's spend a couple of minutes on backpropagation. So we've seen how backpropagation is performed for the regular networks. When you get to bidirectional networks, things get a little more complex, right? So what happens in a bidirectional network is something like this. You're going to have a forward network which computes so you have inputs coming here and which computes some sequence of vectors at each time. Then this thing goes to a backward network, actually, yeah, where the information flow is backwards. And this also computes some sequence of vectors. And at the output, you're going to concatenate these two outputs together. So this operation is actually just a concatenation where you're taking the outputs of the two guys and attaching them one on top of the other. And that's being passed on to the next block. So when you're coming backwards, what happens? When you're coming back downwards, when you get to the output of this block, the derivative is going to be this long, where the upper portion of the derivative corresponds to the backward net, and the lower portion of the derivative corresponds to the forward net. So you're going to have to separate these two components, right? Once you separate these two components, then we're going to use basically the separated components are being shown on the slide. And then for the forward network, you're going to use the specific derivatives, the portion of the derivatives that came to the forward network, at the output of the forward network, and you'd use backward propagation through time to compute derivatives going all the way to the beginning. For the backward network, you're going to use the portions of the derivative that came at the output of the backward network, and now you're going to be computing derivatives going forwards, because it's, you're reversing the order of computation, right? And then each of these is going to give you a derivative with respect. So this one gives you a derivative with respect to the input. This one also gives you a derivative with respect to the input. To the block, the two must be summed, because the input to the block is going out two ways, right? And so finally, the forward and backward partial derivatives are added to get the derivatives with the full gradient for the input. With very straightforward. So I have pseudocode on the slides as well. I'm going to skip that. But just to summarize, we have training recurrent neural. We saw what recurrent neural networks are. Training recurrent neural networks requires defining a divergence between the actual and desired output sequences and back propagating gradients over the entire chain of recursion. This is BPPT, backward propagation through time. And you need to pool gradients with respect to individual parameters to account for parameter sharing. Bidirectional networks analyze networks both ways, from beginning to end and from the end to the beginning. And backprop must follow the chain of recursion, meaning if it's the forward portion of the network, backprop goes the other way. If it's the backward reverse portion of the network, backward goes from the beginning, from the beginning to the end, and the derivatives get added up, right? So we are going to be looking at more about how recurrent networks work, what are the conditions for it to actually behave properly, and how we can extend these models to make them more useful in the next class. So do we have any questions? No. Thank you.